everyone, and welcome to this new lecture on de Moivre's theorem. In this lecture, we'll go through a theorem that is used to find out answers to questions involving the complex number being raised to a certain power. Before we get into this theorem and the application of this theorem, we would go about finding out new stuff about complex numbers, and we would brush up our skills related to complex numbers because complex numbers was actually the first topic that we covered. So it's been a while since we looked at complex numbers. We would go through some of the basics of complex numbers, not the real basics, like not the ABC of complex numbers, but something new related to especially to the graphing of the complex numbers. Once we are done with that, then we would use that to apply complex numbers to new scenarios and new equations. And once we're done with that, we would go in a step-by-step approach into solving of the using of this theorem for solving our questions that we might face. So we already went through the complex plane, in which you talked about that the complex plane is different from the xy plane, because rather than having an x and a y axis, we basically have a real and imaginary axis. So in a real and imaginary axis, you have 2 points, that is the complex number. The real part is plotted with respect to the real axis, and the imaginary part is plotted with respect to the imaginary axis. So this is how basically it's done. So a plus b1 is the way in which a complex number is represented, b being the value of the imaginary part, the complex number, basically the imaginary part, and a being the real number. And this is how you would plot 2 plus 3i. Now, another thing that we studied about during a topic of complex numbers was the concept of absolute numbers, the concept of basically absolute values, that is a modulus of a complex number. So the modulus of a complex number is nothing but the magnitude of the complex number. What you do basically is that you take out the squares of the real part and the imaginary part, and you just underroot that. And once you do that, you would have the basically the value of the modulus. Now what this basically entails is, the reason why we do that is because we form a triangle. We use the x-axis for the real value and the y-axis for the imaginary value of the complex number. So once we have that, so we try to find this out. Now this blue line is actually what is found out through using a modulus. How is this so? Because if you look at this, this is basically forms the hypotenuse, and what we're basically using is the Pythagoras theorem, that is the base square plus the height square and under root, and you would get the hypotenuse. And that is exactly what we are doing over here. That is, if you look over here, a and b are the base and the vertical, the perpendicular, and through that you find out the hypotenuse, which is represented as magnitude, which can be called an R as well. Now, trigonometric form of a complex number is basically used to represent a complex number in form of trigonometric functions. If you look over here, if you look at this triangle with respect to theta over here, theta being this angle over here, you would see that this angle, the length of this side, that is the real value, the value of the real part of the complex number, could be found out by using r, that is magnitude, and cos of theta, cos being the base and the hypotenuse. So the hypotenuse is r and the base is of course a. So cos would be basically cos theta would be base over hypotenuse, and the hypotenuse being cross multiplied, you get this. Just like that, you find out the value of the imaginary part, and the value of the imaginary part is actually found out by r sine theta, sine being perpendicular over hypotenuse, and you cross multiply and you get this value for the y-axis, basically the complex axis over here. So this can be written down in the form in front of you, that is z, that is being the which means the complex number is equals to r of cos theta plus I sine theta. Why is that so? Because r cos theta is equals to a and r sine theta is b. So we're basically writing a plus ib. That is the how we wrote the complex numbers before we went into the trigonometric form of complex numbers. So nothing over here, nothing new is written over here. Basically it's just saying that the tan theta would be the perpendicular over the base, and this is how you would find out in terms of the triangle. Now moving on, now let's just take an example. Finding trigonometric form. Find the trigonometric form with 0 and with theta being from 0 to 2 pi for the complex numbers 1 plus 3i. Now, how are we going to do this? This is a really simple example basically. I mean, the first thing that we have to do is we need to find out the r, because if you look at the trigonometric functions over here, there are basically two things that you need to find out. You need to find out the r, and you need to find out the theta, the angle and the magnitude. These are the two things that you need to find out. In order to find out the r, we take the argument of z, that is, we take the modulus. So that is really easy. What we do is a squared plus b squared. A squared over here is going to be this, and that's going to be 1, and b squared is going to be under root 3 whole square, and that is going to be 3. And once you add those, you're going to get a new answer that is going to be 2. So finding theta. Now in order to find theta, you can find that through a lot of ways, but over here we're using tan, and that is the best way to go about this as well. I mean, you can find it through cos, through sine, but I would say that the best way to find out tan theta is under root 3 by 1. The reason is because these two values you already have that. In order to, you cannot find out in this case, basically you can find out theta anywhere anyway, but in this case it would be really hard for you to find out the theta, because if you use a is equals to r sine theta, you would have to divide, and then you would have to take cos inverse, sorry, sine inverse. So rather than doing that, why don't you just use the simple thing? Why do you have to reinvent the wheel? So you just write out tan theta, and tan theta is going to be under root 3 by 1, and basically that is going to be pi by 3. So this complex form, that is in the complex number in this form, is actually going to be written as this in front of you, that is 2 brackets cos pi by 3 plus I sine pi by 3, with the r being 2 and the theta being pi by 3. So once you're done with that, you have the product and quotient of complex numbers. This is the new thing that we have to find out. Now this is really simple. I mean, you just have two complex numbers in trigonometric forms. They have z1 and z2. Quotient means the division, so you multiply z1 and z2, you're going to get r1 r2, and these angles are actually going to be added in this, because this is actually a product. And in terms of quotient, the magnitudes are going to be divided and the arguments are going to be subtracted. Now one thing you need to know over here is just the condition that r2 cannot be 0, because if anything is divided by 0, we're going to get an infinity, but we don't need to get into that. So this was one of the things that I wanted you to look into. Now let's use this in an example. Express the product of z1 and z2 in standard form. Now the first thing you need to do is that you need to write down the product. In order to write down the product, we use z1 into z2, that is r1 into r2 and cos, and then you find out the arguments by adding these angles. So once you're done with that, you have 4 under root by under root by 2, because you have 4 over here and under root by 2 over here, that is r1 r2, and then you add these, and then you add these. After you have added these, you get the new 4 under root by 2, and then you have in front of you this equation. So what you do over here is that you actually solve this, rather than just writing it down in terms of an argument. You actually solve the angle values. You're going to need a calculator for this. So you find out cos under root 5 pi by 2 12, and you find the answer that's going to be 0.259, and then you do that for the second one as well, 0.966, and then you get an answer which is going to be this. This is basically known as the standard form of the complex numbers, and this is basically called the trigonometric forms of complex numbers. So now that we have that out of the way, now that we understand, now we're going to find out, using this theorem, the fifth thing that we did. We already did the addition, the subtractions, the multiplications, and the divisions. Now we find out basically the power. How to find out the power of a complex number? We find out the power of a complex number through this, that r and then you have this complex number, and it is being raised to any number. Let's just say this is the complex number, that is z to the power of n. Z is a complex number, and you're raising it to the power of n. What do you do? What you do is basically you write it down first as this. Now when you write this down as this, then this has to have an effect on the argument, that is the angle theta, and on the magnitude, that is r. And what is the effect that it has? R is then raised to n, and then cos is being multiplied by n theta, and n theta over here as sine as well. So what does the power have an effect on? Basically the magnitude is raised to that power, and the angle is being multiplied by that power. That is all that there is to this theorem. Now let's try this over here. Now let's just say you have an example in front of you. Now you're raising this complex number to the power of 4, right? So now the argument of z is basically theta, and that is going to be 7 pi by 6. So you've already found out the argument. The argument means the angle, that theta, and then you find out the magnitude by finding out the modulus. So you find out the modulus, and then you have is equals to 1 over here. So this is the value of this, is basically this being represented as this the standard form of complex number is being represented by a trigonometric form over here. Once you're done with that, now we come to the second part of the theorem, the actual part of the theorem that we have to do, that is raising the power. So what did I tell you in the last slide? Basically the argument is being raised, and the argument, sorry, is being multiplied, and the modulus is being raised to that power. So if you look at over here, if you look at this particular complex number, you will see that the modulus over here is 1. So if you raise 1 to the power of 4, it has no value. It's just going to be 1 once again. So the main point that you have to do is that you have to multiply the argument with the power. So the argument was 7 pi by 6. You multiply this by 4 because it is being raised to the power of 4, and after you multiplied this, you get the new answers. That is going to be 14 pi by 3 and 14 pi by 3 once again. Now after that is done, what you do is you write it down as 2 pi by 3, and you also write it down as 2 pi by 3 because we're simplifying it now, and then once again you write it down in the standard form. So now we need to find out the nth root of the complex number. There's nothing complex about it. All you need to do is nth means any root. You can find out the 5th root of the complex number or the 7th root of the complex number. Basically you need to find out any root of the complex number, and the way to do that is that you use this particular form that we're going to be using right now. So in order to find that out, we use a new formula, and basically the old formula, the same theorem that we're going to use with a little bit of difference over there. Now let's just say you need to find out the nth root of this complex number, which is being represented as a trigonometric function over here, the trigonometric form, sorry. So in order to find that out, rather than raising the modulus, raising the modulus to the particular power, we take the under root of the modulus. So we take under root of nr, and over here, rather than just multiplying it, so we write it down as theta plus 2 pi k, and theta plus 2 pi k over n. Now theta and k could be any of these things, and these will be the nth root of the complex number. This is basically the 6th root of the complex number. Let's just find out the answer to this. Now this question in front of you is that find the cube roots of 1. Now don't get confused by this. This is a really simple question. Now we did one of the things in the complex number, that this number, real number, this is also a complex number. The only difference between this complex number and any other complex number is that this complex number does not have an imaginary part. The imaginary part of this complex number is basically 0. So we write this down, and in order to write this down, what we do over here is that write 1 in the complex number form. Like I said, we write it down. So once we have 1 plus 0, so we take out we use the tan to solve this, and we get perpendicular over base, that is we get 0 over 1, and this is what we get, cos 0 plus I sine 0. The third roots of 1 are the complex numbers. So once we already have theta is equals to, now you see this is a very unique question. Over here the problem that you're going to face is that the theta is going to be 0 and the modulus is going to be 1. So you don't need to write anything other than these terms which are already inside. So how do you write this down? You write theta plus 2 pi k over 3, because we're going to find the cube roots, and cube means 3. Now for k we use 0, 1, 2 because we start from 0. So if we write it down as 0, we're going to get cos 0. We write it down as 0, we get sine 0, and cos 0 plus sine 0, one of these is 1, we get 1. Then we move forward. Of course 0 has no value. Then we write down 1 over here, we get 2 pi by 3 over here and 2 pi by 3 over here, and then we actually solve this so we can write it down in the standard form. Once we're done with that, we go to the third part, and then we get 4 pi by 3, and in 4 pi by 3 we get 4 pi by 3 plus I sine 4 pi by 3, and this is what we get in the end. So it is pretty straightforward. There's nothing to worry about. Just remember, you have to do it in a step-by-step way. All there is to these complex numbers and this theorem is that you need to find out the modulus, you need to find out the argument, And if it asks to raising the power, you just raise the power in the modulus, and you just basically add in the multiply in the argument. And if it has to find the nth root of any particular thing, you take the under root of that modulus depending on the root, and basically you use this particular formula to find out the nth root and the inside the argument of this particular complex number. So this is pretty much it for this, and hopefully I'll see you in the next video.